Am I audible?
Yes, sir.
Okay. So let's start it. So hello, I'm Himanshu Mishra. So this week we will be doing some problems related to the heat convection. So this week we'll be doing some very basic problems related to the heat convections, such as averaging the heat transfer coefficients and solving some problems related to the boundary layer and finding heat transfer coefficient in those cases. So last week we had solved some problems related to the transient heat conduction, where we use mostly lumped heat transfer analysis into the problems. We solved one problems related to the semi-infinite body. So this week also in this tutorial also I will solve some couple of problems related to the semi-infinite body that we will do in the end. And one question I will solve related to the long body, which is related to the transient heat conduction problem. So,
Actually, sir, some disturbance is coming continuously.
okay. Hello, is it fine now?
Yes, it has reduced a little bit.
Now?
I think it is okay now.
Okay. So yeah, I was saying that so this week also we will solve some couple of problems related to the semi-infinite body and one from a long body. Both are related to the transient heat conduction problem. We begin with the some questions related to the heat convection problems, and then in the end we will just wrap it up the transient heat conduction problems. So let's start with the first question here. So in the first question, we have in a flow over a surface, velocity and temperature profiles are of forms. We have given the velocity and the temperature profiles, and where the coefficient A and G are constant, or A through G are constants, obtain expression for the friction coefficient CF and the convection coefficient H in terms of U infinity and T infinity, and appropriate profile coefficient and fluid properties. So in this question we have a, let's say, flow past a surface. So this is my surface and this is my flow. So there is a boundary layer and there is a velocity profile due to this boundary layer. And we have a temperature profile also. So we have given the temperature profile as and the velocity profile is given as we need to determine the drag coefficient and the convection coefficient. So let's first find the convection coefficient H. So in the boundary layer problem, we know that whatever the heat transfer that will occur at the surface will be equal to the heat transfer that is occur due to the convection just above the surface. So from this principle, we can write our heat transfer equation as so this will be my heat transfer equation, and from here I can uh, find my heat transfer coefficient. Using this relation. So we need to determine the derivative of our temperature profile. So the derivative of the temperature profile at y equals 0 will be E 2Fy 3Gy square, and at y equals 0 it will be just E. So we can plug this in this expression and we will get the heat transfer coefficient in terms of T infinity and E, where E is a constant. So this will be my heat transfer coefficient. Now to calculate the friction coefficient, so this is a concept that I am taking from the fluid mechanics course. So in the fluid mechanics, we define the skin drag as so here CF is the skin friction coefficient, F is the force, rho is the density, U is the velocity of fluid, and A is the area over which the fluid is flowing. So this skin drag actually measure the drag force whenever there is a flow past the surface. So when there is a flow past the surface, it will experience some kind of a drag on the surface, and that drag is given by this formula. So also we know that we can write the definition of a stress as force per area, which means that we can write the expression of a shear stress. This is the stress which is caused by the drag. So when there is a fluid flowing over the surface, it will cause some stress over the surface, some shear stress over the surface, and that is similar to this shear stress that you encounter in the boundary layer problem, that whenever there is a flow, it will rub each subsequent streamline over each other, and this is which result into the shear stress. And due to the shear stress, there is the velocity and the temperature, velocity profile. The highest shear stress occur at the surface of the wall, which means there is a rubbing of fluid particles over the surface, which result into a net stoppage of the fluid parcel. And yeah.
So can you elaborate the difference between viscosity and drag?
So viscosity is a property of the fluid. Based on the property, it can experience, it can offer you a different forces or the different stress. Drag is just a force uh, that experience by the system or the wall. Now, how much amount? Uh, uh, what is the amount of the drag force that the wall will experience will depend on the several properties and the uh, physical parameters. One of those properties is the viscosity, which is the property of a fluid, uh, which define how it how the particle with rubbing with each other. For example, if there is a fluid with a low viscosity, the shear stress or the force drag force will be low. But if you took any fluid with a higher viscosity, it will experience the higher drag force. So viscosity is just a property which defines the rubbing action, whereas force is, I mean, some physical parameter uh, which amount to that, what to say, which is happening, like which amount to the stress which is going on. It is action actually which is going on when there is a flow past the surface of a body. Is it
Okay. Okay,
making
sir.
sense?
Okay.
So here, yeah, we can write the expression of a shear stress as CF rho u infinity by 2. And from the Newton's law, we can write shear stress at the wall as du by dy at y equals to 0. So we need to take the derivative of this velocity profile at y equals to 0 to define the shear stress at the wall. So and at y equals to 0, it will be just A. So my shear stress will be mu A. This is my shear stress. So now I can use this relation to define the drag coefficient. So mu A CF will be 2 mu A by rho u infinity. So this is my expression for the drag coefficient, and this is my expression for the heat transfer coefficient that we obtain from the given velocity profile. So in this question, we have given the velocity profile and we need to find the drag coefficient and the heat transfer coefficient. And to do that, we use, to find the heat transfer coefficient, we use the relation where we equate the heat conduction at the wall to the heat convection into the boundary layer to find the heat transfer coefficient. We take a derivative of a temperature profile to evaluate the heat transfer coefficient. And to find the drag, we use the drag force relation. And to find the shear stress, we use the Newton's principle to find the shear stress at the wall. And then using the drag expression, we find the drag coefficient here, CF. So, any question, any doubt in this question?
No, sir.
Okay. So then let's move to the next question. So one way to answer that the question you asked about the force versus viscosity is that there is a simpler explanation that I am thinking as of now. So the viscosity can be act as a property. For example, there is a, let's say, a fluid parcel, and within it, if we magnify this fluid parcel will so the molecule inside this fluid will have some rubbing action, and due to the rubbing actions they can cause a force or some dissipation. So that force will we can categorize as a drag force, because since there is a rubbing action, there is a transfer of momentum between those molecules, because one molecule is transferring their momentum to the other molecule, and due to the net change of that momentum, there will be a force, and that force will be the skin drag force that we have just defined here. And the property by which those atoms or those molecules are rubbing into each other, that property can be defined as the viscosity. Is it more clear now?
But then how we can relate it with drag?
We can relate it by a drag by this shear stress equation from the Newton's law, because drag force and the shear stress are interrelated to each other. Stress is just a force per unit area. That's it. And you can relate it to the viscosity by using the Newton's law.
Okay, sir.
So let's move to the next question. So here we have a laminar flow over a flat plate, and the local heat transfer coefficient Hx is known to vary as x to the power minus 1 by 2, where x is the distance from the leading edge, x equal to 0 of the plate. What is the ratio of the average coefficient between the leading edge and some location x on the plate to the local coefficient at x? So here we need to define the average heat transfer coefficient. So we have given the local heat transfer coefficient. So let's say there is a boundary layer, and as we know that as the boundary layer is developing, the heat transfer coefficient will be changing as we are going right to the x direction. And how it is changing, it is given in the question. It is changing as x to the power minus 1 by 2. So c is just a constant. So in the question it is given that hx is proportional to 1 by 2, and
Excuse me, sir.
yes,
This that convection coefficient is changing. So this change of value will be within the boundary layer, or this change of value will be outside the boundary layer also?
no, it will be within the boundary layer only, because outside the boundary layer there is no velocity profile or the temperature profile is there. So the temperature is uniform outside the boundary layer. So only inside it will be changing along the x direction.
Okay.
So we can use the relation HTA. So on simplifying this relation, we can get write the average heat transfer coefficient in terms of local heat transfer coefficient. Now, since we are dealing with the external flows or external boundary layer flows, we don't require the area to be defined. We just write in terms of the length of the problem, because we usually assume that the weight is per unit or the unity. So I can define my average heat transfer coefficient as in terms of x only. So we just need to integrate it, and my hs is given as dx. So I can write. So after integrating it, I can just directly write this. So my h bar will be 2cx minus 1 by 2, and cx minus 1 by 2 is my locally transfer coefficient. So it will be h bar 2hx. So my average heat transfer coefficient is just twice of the local heat transfer coefficient, which means that if I plot the hx and h bar over x, my local heat transfer coefficient will be varying like this by 2, and my average heat transfer coefficient will be varying like this. This is my h bar 2 proportional to 2x, and this is proportional to x to the power 1 minus x to the minus 0.5. So yeah, this is just a straightforward question. So we already have given the local heat transfer coefficient, and we asked to define the average heat transfer coefficient over the plate. And so we integrate it from 0 to x, and we find the average heat transfer coefficient over 0 to x on the plate, which is twice the heat transfer coefficient, local heat transfer coefficient. So
So this integration, that 1 over x0, that can you explain this, sir, how we have integrated?
You can integrate it over the length also. If there is a length given, like find the heat transfer coefficient till L is equal to, let's say, 1 meter, then you can integrate it over 0 to 1. But in the question, we don't given any length. We have just given some random distance x. So we just integrate from 0 to x. That's it.
What about the 1 over x, which is lying outside the integration?
Yeah. So just take it inside and integrate it.
Okay.
Yeah.
Okay.
So let's solve something similar problem again. So again, we will have a laminar free convection problem and convection from a heated vertical surface. Our local convection coefficient again expressed in terms of x to the power minus 1 by 4, and we have given hx is the coefficient at a distance x from the leading edge of the surface, and the quantity c depends on the fluid properties and is independent of x, so c is the constant. Obtain an expression of average heat transfer coefficient to the local between the leading edge x equals 0 and the x location. So basically this is the same questions, but just a slightly different heat transfer coefficient, local heat transfer coefficient. So we will using the same integral to solve it. So in the question again, it is given that we need to find the average heat transfer coefficient from x equal to 0 till x. So we will be integrating from 0 to x again. And this is so after integration we can write C 4 by 3 by 4, and this is the local heat transfer coefficient, 4 by 3 Hx. So again, I can write my average heat. So this time our average heat transfer coefficient is 4 by 3 of Hx, and we can plot a similar curve here. So this is my Hx proportional to x to the power minus 1 by 4, and this is my average heat transfer coefficient curve, which is proportional to 4 by 3 minus 1 to the power 4. So simple problems where we have given the local heat transfer coefficient, and we just need to find the average heat transfer coefficient. So we just integrate over from 0 to x or some L location, and we just, after integration, we will be getting the average heat transfer coefficient relation. So any doubt in the third and second and third question?
No, sir.
Okay. So the next question is a circular hot gas jet at T infinity is directed normal to a circular plate that has radius R naught and is maintained at a uniform temperature Ts. So the gas flow over the plate is axisymmetric, causing the local convection coefficient to have a radial dependence of the form HR, given in terms of A plus B R to the power n, where A and B are the constant. And we need to determine the heat transfer to the plate in terms of T infinity, Ts, and constant. So we have given a circular plate, and there is a gas which is blown to the circular plate, and the temperature of the plate is Ts and T infinity, and there will be a convection heat transfer, and we have given the heat transfer coefficient in terms of some constant and the radial direction, and then we need to find the total heat transfer. So let's say this is my element area. So there will be a heat convection heat transfer. My gas temperature is T infinity and my surface temperature is Ts. And since my heat transfer coefficient is given in terms of geometric property, my convection heat transfer will be, I can write in terms of an integral, which is now my element area dA. So this is my dA, can be written as 2 pi r dr because it's a circular plate. So my heat transfer will be dr. So I can pull out some constant out of the integral. need to take integral of this. So it will become, the first term will become a r square by 2, and my second term will be b so it will be so I can put the limits inside the bracket. A r naught square by 2 plus b r naught so my heat convection will be 2 pi Ts minus T infinity so this will be my total heat transfer over the plate, and I can define my heat transfer relation in terms of Ts, T infinity, A, B and R naught, which is Ts, T infinity, R naught, A, B and N. So this is kind of a similar problem. We have given the heat transfer coefficient, and we have been asked to determine the heat transfer in the circular plate. So we have done the similar thing here. So we use heat transfer in an element area to this expression which defines the heat transfer in an element area. We integrate this expression here for the circular sheet to determine the total heat transfer in the circular sheet. So it's and everything else is just a mathematical simplification. So any doubt in this question?
Sir, you have taken area dA 2 pi r dr. So it means the heat loss through the edge only we have considered. Then how
Yes.
can we?
Yeah. So because this is a convection heat transfer, so there will be a heat transfer from the gas to the surface. So this is my circular sheet, and imagine there is a gas above the circular sheet which is flowing, and there will be a heat transfer from this gas over the entire circular area. So my area will be pi r square. So if I write in a differential form, it will become 2 pi r dr.
That heat transfer in the statement says it is normal to like a circular hot gas jet T infinity is.
Yeah. So this is my normal. For example, let's say I'm drawing the inclined circular plate, and this is my normal, and there is a gas flow above the circular plate. This. So gas will be in the contact of an entire circular cross-sectional area, which is pi r square. And we have to
just that you just show the statement that statement hot gas jet at T infinity is directed normal to the circular plane. That means your jet is directly to the 2 pi r square, isn't it?
No, it will be, yeah, sorry. So in that case also, yeah, it will be pi r square only. So if my jet is like So if my jet is like this, so it will be expanding over the entire cross section area of the sphere. So here you need to consider the area where there is a complete connection of a fluid with that area. So even if it is normal to the surface, for example, let's say this is my phone. So there is a heat transfer like this, so it will expand into the entire body like this. So it will go to the entire span of the circular sheet. It will go uniformly in the all direction, covering the whole pi r square area to that. So even if the flow is like that, which I have shown above like this, you need to consider the overall pi r square area, because there is a contact of a fluid with the whole cross section area of the circular sheet. So you need to consider that contacted area. So even in both cases, like in this case and in this case, the fluid is over the whole area, cross section area of the sheet, and therefore you need to consider the pi r square. Now, since you have taken the elemental area, you write the differential area in terms of a 2 pi r dr, which is you just differentiate pi r square in terms of r, and you write in terms of you get in terms of 2 pi r dr, and you just use into the equation here.
But sir, if it is that gas is flowing perpendicular to the surface area, then won't it be a problem of flow past circle or flow past cylinder?
Yeah. So it is a problem of a flow past a circle. For example, my jet is going like this, and once it reaches the circle, it will expand into every direction, like here, like here, like here. So it will expand into every direction uniformly. So it will cover all the pi r square area, all cross sectional area of the plate. So first jet normal to the sheet. Once it reaches the sheet, it will just spread over the sheet, and that spread area is the cross sectional area.
So in that case, the equation we are using is will it be correct that when
Yeah. So you just need to be ensured about the spreading area. That's it. So even in this case, let's say this is my first case, my pi r square is my contact area or the spreading area. And even in my second case, when there is a normal flow and then it spread out uniformly, my contact area is my spreading area. So you just need to be ensured about the contacted area, and that's it. Once you know what is the contact area, you can use this relation for general purpose, for general heat convection problem.
okay.
Yeah. And R naught is this distance. So this is my R naught, and this is my zero. So yeah. Because in the circular plate, there is a very unlikely situation where you cannot use pi r square relation, because it's a two-dimensional geometric problem. So even if it is a norm, even if the flow is normal to the circular plate, or even it is along the circular plate, you need to consider in both the cases you need to consider the cross sectional area pi r square, because this is the contacted area for the gas which is flowing over the surface or normal to the surface, because after getting hitting it is spreading in all the direction.
Okay, sir.
So even in the three-dimensional geometry, the surface area will be same. It doesn't matter the direction of the flow, and that is actually a advantage of having a sphere or the spherical or the circular surface, because the area will always be the same, irrespective of the direction of the flow.
But sir, this expression we are doing when the flow is parallel to the plate, then whatever expressions we are driving, they are in for the boundary layer, isn't it?
No, this expression is not from the boundary layer. Here we are not considering the boundary layer at all in this question. Earlier in the earlier question we use the concept of the boundary layer, but here it is just a plain simple heat convection problem. That's it. There is no boundary layer at all.
So the turbulence and laminar will not matter here.
No, 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 no. Any turbulence, all these concepts are not material. It is just a plain heat convection problem. And in the problem, we just given that the heat transfer coefficient is a function of the radial geometry, and that's it.
Okay.
Yeah. So unless we have given the velocity, or we have directly given that the flow become turbulence, we do not need to worry about it. So if we have given the velocity, we can just use the Reynolds number formula to determine the magnitude of this Reynolds number, and from that we can able to judge whether the flow become turbulent or it will always be in the laminar region.
But sir, when the flow is perpendicular to that normal to the surface area, then in Reynolds number calculation we consider the length. So I think that will not be how we can then determine the Reynolds number when that flow is perpendicular to the hot jet directed normal to the circular plate. When it is normal to the circular plate, then Reynolds number length is required. The length is not there then.
So in that case, you need to consider where you want to evaluate your condition of a flow. So in that case, your flow is normal to the circular sheet. Let me draw some other configuration. So let's say this is my side configuration, and this is my top configuration, and this is my plate. So the jet is coming from top normal, and then it spreads over the uniform. It hit the surface, and then it spreads over the entire surface. Now you need to define where you want to evaluate the condition of the flow. So the condition of the flow you need to evaluate at the surface of this circular sheet. So you need to define the condition here at the circular sheet. So here at the circular sheet, you need to define the Reynolds number. So the Reynolds number in that circular sheet will be the radial property. So here A will be the R naught in this case, because the flow is actually spanning over the circular sheet, and if it becomes turbulent, it will become turbulent at the circular sheet so there will be some laminar flow. So when it moves across the circular sheet, there will be some laminar flow up to some distance, and after some distance it becomes turbulent in nature. So basically you need to determine the geometric property of that surface. In this case, the surface is a circular sheet, so my geometric property A will be R naught in this case. And the velocity will be the velocity, which is velocity of a flow, which is expanding over the circular sheet.
Okay, sir.
Yeah. So it is clear, right?
Yes, sir.
Okay. So the next question is the air at a free stream temperature T infinity at 20 90 degrees Celsius is in parallel flow over a flat plate of length 5 meter and temperature Ts equals 90 degrees Celsius. However, obstacle placed in the flow intensity mixing the increasing distance x from the leading edge and the spatial variation of temperatures measured in the boundary layer is correlated by expression. So we have given the temperature profile in terms of x and y. Now determine and plot the manner in which the local convection coefficient varies with h. Evaluate the average convection coefficient. So this is again a similar problem. So here we have given the temperature profile instead of a locally transferable coefficient. So now we have a boundary layer over the flat plate. There is some boundary layer, and the temperature variation is given in terms of the uniform temperature or the temperature outside the boundary layer is 20 degrees Celsius, and temperature at the surface is 90. So there will be a heat transfer from the surface to the next subsequent layer by the conduction, and within the fluid there will be a heat transfer due to convection. So we can equate the same relation. So this is at surface, this is within fluid. So when I take the derivative of temperature profile at y equal to 0, I will get minus 70 600 x. So since it is at y equal to 0, it will be just exponential to the power 0, which will be 1. So my heat transfer coefficient will be K Ts is 90 and T infinity is 20. So my heat transfer coefficient will be, on solving this, I am getting the heat transfer coefficient as 17x K. So this will be my heat transfer coefficient. So now I need to find the average heat transfer coefficient.
No, sir, this H will be 600 XK, I think.
Is it? Yes. 600 XK. So now I need to find the average heat transfer coefficient from length 0 to 5 meter. Yeah. So we have given the length of 5 meters. So we will take the integration. Dx 1/5 600 xk dx. So since we are assuming here that our thermal conductivity is a constant, so we can write 600k by 5 x dx, and it will be 5 x square by 2. 5 is, we just need to put the limits, so we will get and here we can write 25, so it is 60 multiplied 25k. So this will be my average heat transfer coefficient, and the local heat transfer coefficient I get from just my energy balance equation, which is this. So in this question we have given the temperature profile, so we need to find the local heat transfer or local heat transfer coefficient first. For that we need to use the energy profile or the energy balancing equation, and once we get the local heat transfer coefficient, we just simply integrate it over the length from 0 to 5 or 0 to L. So this is my L to get the average heat transfer coefficient relation. So any doubt in this question?
No, sir.
Okay, so let's move to the next question. So in the next question, the sketch the variation of velocity and thermal boundary layer thickness with distance from the leading edge of the flat plate for the laminar flow of air, water, engine oil and mercury. For each case, assume a mean fluid temperature of 300 Kelvin. So here in this question, we need to roughly sketch the thermal and the velocity or the hydrodynamic boundary layer for air, water, engine oil and mercury. And the fluid temperature is a mean temperature. That means the properties like viscosity, density is not changing with the temperature. I mean, we can just consider the average properties. So in this question, we can roughly estimate the hydrodynamic and thermal boundary layer by using the Prandtl number, which is a ratio of molecular diffusivity to the thermal diffusivity. So it is, or we can define the Prandtl number as a hydrodynamic boundary layer thickness to the thermal boundary layer. To the power 1 by n. Here n is the constant. So Prandtl number basically says that which type of a boundary layer will be dominating. For example, if my Prandtl number is greater than 1, in that case my hydrodynamic boundary layer will be greater than my thermal boundary layer. And if my Prandtl number is less than 1, in that case my thermal boundary layer will be greater than my hydrodynamic boundary layer. For gas case, most of the gas case, when there is a flow of a gas past the surface, the Prandtl number is actually approximately equals to 1, which says that my thermal boundary layer roughly equals to my my hydrodynamic boundary layer roughly equals to my thermal boundary layer. So on the basis of my Prandtl number, magnitude of my Prandtl number, I can just judge which boundary layer is dominating in the problem. So let's say for air, my Prandtl number is roughly around 0.75, let's say. So in that case, I can just so for 0.75, let's say this is my hydrodynamic boundary layer. So within my hydrodynamic boundary layer, there will be a variation of velocity normal to the surface. And since it is 0.75, that means my hydrodynamic boundary, sorry, thermal boundary layer is just little bit uh, greater than my hydrodynamic boundary layer. So it will be just above my hydrodynamic boundary layer. So blue line is my thermal boundary layer, and red is my hydrodynamic boundary layer. So blue justifies the variation of temperature. This is my flow surface. And this is my properties of the outside. Similarly, for the water, my Prandtl number is, let's say, roughly it's equal to 6, which means that my hydrodynamic boundary layer will be greater than my thermal boundary layer according to this relation. So this will be my hydrodynamic boundary layer, and this will be my thermal boundary layer. For engine oil, my Prandtl number is around 6500 approximately. So in that case, again, my hydrodynamic boundary layer will be very, very great, larger than my thermal boundary layer. So if this is my hydrodynamic boundary layer, then comparatively, this will be my thermal boundary layer. And for the mercury, my Prandtl number is 0.025. So again, according to this relation, we can say that my thermal boundary layer will be very much larger than my hydrodynamic boundary layer. So this is my thermal boundary layer, and this is my hydrodynamic boundary layer. So based on the Prandtl number, we can just figure out which boundary layer is dominating in the problem. So any issue in this question?
No, sir.
Okay. So let's solve the next question. So here we need to choose a correct option. So the first option is the buoyancy force is the primary driving force for the free convection. Okay. My next statement is free and forced convection can never occur simultaneously. Okay. C option is there are situations where the contribution of both free and forced convection are taken into account simultaneously, but the direction is always opposite for each other. So can you guess which might be the correct option? So the first option is first option is the buoyancy force is the primary driving force for the free convection. So is it the correct option?
Sir, if it is due to that density difference, the temperature difference, then it is correct.
Yeah, so my option is correct. My and what about option B? Free and forced convection can never occur simultaneously.
I can't tell, sir.
Well, this might not be the case because forced convection can happen with the free convection. So for the free convection, there is a restriction that it happens when there is a density change or the temperature change, and due to this, that only the free convection occurs. But for the forced convection, there is no such restriction. In fact, we just need to push the fluid over the surface, over any surface, and we will have a fluid force convection, and at the top of it we can have a free convection also. This option is not the correct option. The C options, the option number C is there are situations where the contribution of both free and forced convection are taken into account, but the direction is always opposite for each other. Is it correct?
Sir, if B is incorrect, then C should also be incorrect.
No, so B actually says that force and free convection can never happen at the same time. But but the option C is it can happen at the same time under some conditions. So B is incorrect because it can happen at the same time. Force and free can happen, so which means that there is still option of still there is a hope for C that it might be correct or incorrect. Sorry, you need to consider the additional thing in the C. Like, what is the direction of force and free convection? Is it always opposite, or it can be in the same direction?
I think C is also incorrect because forced convection can be parallel to the surface, but the natural convection will be perpendicular.
So the force convection can be parallel to the surface, but so for the free convection, there is always a predefined direction, and the direction is where the density of air is changing. So if my density of upper part is reducing, sorry, it become heavy, it will come down and it will replace the light fluid parcel. So my free convection will always have a direction which is upside. But what if my free convection has a direction of downside? It is still parallel to the surface. So here, force and free, they are still parallel to the surface, but they are in the opposite direction. Is this situation is possible?
No, sir. This free convection, that means our fluid will be rising from the surface towards upside, or it will be coming down.
Yeah, so it will be rising to the surface, and the direction of the heat transfer will be along that, right?
Yeah.
Yeah, for the free. But in the force, yeah.
But in case of forced direction, that direction of heat flow we are talking, or no, this.
Yeah, we are talking about the direction of the heat convection.
In forced, it will be also. It can be like both ways, like in.
For the force, it can be in both ways. So there is no predefined direction for the force because we are just forcefully supplying the air current or the fluid current to the system, and based on the interaction of fluid current with the solid surface or with some other fluid parcel, there will be a heat convection. So for the force convection, there will be a no predefined direction, but for the free convection, there is a predefined direction. So it is not always necessary that they should be opposite of each other. They can be at the same direction or they can be at the opposite direction also. And
Yes,
they
so the C should be incorrect then.
Yeah, so the option C is incorrect. The first part of the statement is can be correct because they can occur simultaneously, but it should not be necessary in the opposite direction. It can be in the same or in the negative direction. So based on the upper option, we can have a D also incorrect option. So the A is the correct option for this problem.
So I think C is incorrect because word always is there. If the always would should not be, if
Yeah,
would not be have, then I think it was possible.
yeah. So because there is a multiple condition with the force and free directionality of force convection, and because of this multiple cases, yeah, the option C is incorrect. So let's move to the next question. So in this question, the flow of oil in a general bearing can approximated as parallel flow between two large plates, with one plate moving and other is stationary. Such flows are known as quick flow. Consider two large isothermal plates separated by a 2 mm thick oil film. The upper plate moves at constant velocity of 12 meter per second, while the other plate is stationary. Both plates are maintained at 20 degrees Celsius. Obtain the relation of the velocity and temperature distribution in the oil. Determine the maximum temperature. So in this question, we are given a quick flow. So quick flow is a specific flow arrangement where your one of the plate, let's say your bottom plate is stationary, but the top plate is moving in some direction. So this plate is not stationary and moving with velocity v naught in the right hand side. So there will be a linear velocity profile due to the movement of the upper plate. So this arrangement is known as quick flow. So we need to determine the velocity and the temperature distribution for this quick flow arrangement. So to solve for the velocity distribution, we need to solve the momentum equation. So in the quick flow configuration, there are certain assumptions we need to follow. For example, the variation of velocity in the x direction will be 0. The variation of velocity in the y direction will not be a 0. And in this quick flow, in this arrangement, there is the pressure, change in pressure along the length L is 0. That means this flow is not driven by the pressure difference, 0. So the flow is actually driven by the top plate only. So my x momentum equation will be now when we use this three relation, I can say that this term will be 0 because there is no variation of velocity in the x direction. So this is my x and this is my y direction. And two more assumption is my vertical velocity will be 0 and my horizontal velocity will not be a 0. So this will be 0 again because my vertical velocity is 0. This is 0, and my pressure in along the spatial direction x will be 0 again. So we will have, so now this is the governing equation for the fluid flow. So to determine the velocity profile of the fluid flow, we need to integrate equation 1. So on integrating equation 1, I'm just directly writing the solution. So to determine C1 and C2, we need boundary condition. So let's say this is my y equals 0 and this is y equals L. So at y equals 0, my velocity is 0, which means my C2 is 0, and at y equals L, my velocity is V, which means that my C1 is V by L. So my velocity profile will be V by L phi. So this will be my velocity profile or the variation of the velocity in fluid flow. Now we need to find the variation of temperature. So for that we will be solving the energy equation. So I will just write the simplified version of the equation with assumption. So this is my energy equation. So on simplification, I can write this as V by L square. So I just plug the velocity profile into this and differentiate my velocity profile to get this. So on integrating this equation number 3, I can write my temperature variation as okay, let me do step by step. So when I integrate this for the first time, I can write this as y plus c1. Now again integrate, creating the same equation. I can write my temperature profile as k y square plus c1y plus c2. Let me write this as c3 and this is c4. So to obtain c3 and c4, we need to use the boundary condition in terms of a temperature. So let me define the boundary condition here. So here my temperature is, so it says that both plates are maintained at 20 degrees Celsius. So both plates have, let's say, are at the same temperature. So let's say my T naught is the 20 degrees Celsius. So at this will give C2, and at y equals L, I will get from equation 4, this is my L square, C3L plus T naught. Oh, sorry, this is C4. So I can find C3 as mu by K V square. So C3 will be, so this will be my C3. So I need to put C3 and C4 in equation 4 in my temperature profile. So my temperature profile will be minus mu by K y square mu by K V square by L y plus T naught. So I can simplify this. So this will be my temperature profile. So we got the temperature profile and we got the velocity profile. So our next step to define the maximum temperature. So in the last tutorial, I defined that to find the maximum temperature, we need to find the slope of the temperature profile and equate it to 0. So from that, we can get the location of the maximum temperature. So once we get the location of the maximum temperature, let's say my location is Ym. So this I get from when I equate my slope of the temperature equals 0. So once I get the Ym, I can just put my Ym in equation number 4 to get the maximum temperature. So I differentiate the equation 4 to determine dt by dy or slope of the temperature profile. Which is 0, and I need to define the location. Equals 0. So my location is L by 2. So at L by 2, my temperature will be the maximum, which means my temperature at L by 2 will be C3 is, this is my C3. So when I simplify this, my temperature at L by 2 will become, on just simplification of this expression, so this is my maximum temperature. So yeah, in this question, we have given the description of the fluid flow, and we have given the boundary conditions that the top plate is moving at velocity with 12 meter per second, and the temperature of both plates are at the temperature of 20 degrees Celsius. And we need to find three things: velocity profile, temperature profile, and the maximum temperature. So for the velocity profile, we use the momentum equation. We simplify the momentum equation according with the approximation. So in the fluid flow, we use a basic approximation, and you can find this approximation in any standard fluid mechanics books. The first approximation is the variation of the velocity in the x direction is zero, and the flow is not driven by the pressure gradient. So the pressure gradient is also zero. The vertical velocity is also zero, and we use this approximation in the x momentum equation to write the governing equation for the fluid flow in terms of velocity. When we solve this equation, I can write my velocity profile in terms of constant, and based on the boundary condition which is given in the question, I can obtain C1 and C2, and I can write my velocity profile, which is a linear in nature for the fluid flow. To find the temperature profile, we can use the energy equation. So I here directly use the simplified energy equation with basic approximations. And on solving the energy equation, I can write my temperature profile. And to solve this constant C3 and C4, I need to use the boundary condition in terms of temperature, which is again given in the question. So then I can write my temperature profile in terms of y, how the temperature is varying in the y direction. Now, once I get the temperature profile, to define the maximum temperature, we need to take the derivative of the temperature profile, which is a slope of the temperature, and we need to equate the slope, which is dt by dy equals to 0. From there, we can define the location where the temperature is maximum. We get L by 2, which is the location of a maximum temperature. And at L by 2, we need to find this temperature, which is the maximum temperature. We can do the same thing for the velocity. To determine the maximum location of a maximum velocity, we need to take the slope of the velocity. We need to calculate the slope of the velocity and equate it to zero. And we get the location where the velocity is maximum. Let's say the location is ym. We put the location ym in the velocity profile of the Kuwait flow, and we can find the maximum velocity. So, any doubt in this question?
No, sir.
Okay. So, by the way, for the Kuwait flow, the location of a maximum velocity is always at the top surface. So, at the top surface, only the velocity will be maximum. That means, in this case, the maximum velocity should be 12 meter per second. So let's move to the transient heat conduction problem. So we will wrap it up today. The few couple of problems of transient heat conduction. So last week we solved problems related to the lumped heat transfer, and we solved one question from semi-infinite plate. So we will solve some couple of problems from semi-infinite plate, and we will wrap this topic. So in this question, we have two large block of different materials such as copper and concrete have been sitting in a room having a temperature of 23 degrees Celsius. This is the room temperature for a very long time. Which of the two blocks, if either will feel colder to touch? Assume the blocks to be semi-infinite solid and your hands to be at temperature of 37 degrees Celsius. So this is the case of a semi-infinite solid, and the general heat transfer relation for the semi-infinite solid can be given as so this is the general expression for the heat transfer for the semi-infinite solid, and my alpha is the thermal diffusivity, which is K by rho C. So we need to tell when we touch the two blocks which block will be more cooler. So we have given two blocks, copper and concrete. So let's see. This is my copper. And for the concrete, same thing. So my heat transfer actually proportional to K rho C. So rho C I can get from there when I put this thermal diffusivity relation here. So I can write copper by concrete as for copper for concrete. And since we have given the material, we can just write down the properties of the material. So my thermal conductivity of the copper is 401. The density of copper is 8933. All these are in the SI units, and my specific heat is 385. And for the concrete, my thermal conductivity is 1.4, density is 2300, and my specific heat is 800. So on just solving this, we will get 22.1. That means my heat transfer or the heat flux in the copper will be greater than heat flux in the concrete. That means the temperature in the copper will quickly come down, and my copper block will feel much colder because due to my higher heat flux rate inside the copper. So here in this question, we need to decide. Basically, we just need to find out the heat transfer comparatively in copper and concrete. And we are given the condition that the both blocks are can be treated as a semi-infinite solid. So we use the relation for the semi-infinite body, and we use for both copper and concrete to find the comparative heat transfer rate. So we found that heat transfer in the copper is 22 times greater than heat transfer in the concrete, which makes that after some time, you will, when you touch the copper block, you will find that copper block is much cooler than the concrete block. And for all the semi-infinite solid, you can use the same heat transfer relation. So, any doubt in this question? So basically, it is just using the expression. That's all. So in the semi-infinite body, we just need to use this expression to solve all the heat transfer problem.
Sir, what about the time t?
Yeah. So when you inspect the two blocks, you touch both at the same time. So we are basically assuming the time for both the blocks are same. So we just cancel the time because when you divide the copper and concrete heat transfer relation, the time will be same. So it will be cancelled out. So it pi L for t, pi L for t. So here time will be cancelled out because you touch the both block at the same time. And since alpha is just a properties of both the blocks, so it will be different. And you can cancel pi and t. So you will be remaining with only properties of the block.
Sir, actually, this Q proportional to K rho C.
Yeah.
Okay, okay, sir.
So this came
Okay, okay, yeah.
when you put alpha here. So you can write here k by rho c, and k is above also, so it will become root k. And one.
Yes, clear, clear,
Yeah.
sir.
Yeah. So we can solve the similar question again. So this is the same question with a similar question with a semi-infinite body. So asphalt pavement may achieve temperature as high as 50 degrees Celsius on a hot summer day. Assume that such a temperature exists for the pavement when suddenly a rainstorm reduces the surface temperature to 20 degrees Celsius. Calculate the total amount of energy that will be transferred from asphalt over 30-minute period in which the surface is maintained at 20 degrees Celsius. So, assuming this as a semi-infinite body, we can use the same relation that we have just discussed. So here alpha is my thermal diffusivity. Now the question says that we need to calculate the total heat transfer over 30 minutes period. So my total heat transfer will be the integral of all the heat over 30 minutes period of time. So here t is my, this upper limit is my 30 minute. So my total heat transfer dt. Now when I integrate this, it will be k ts minus ti root pi alpha, and it will be 2 t1 torch. This is my total heat transfer, and t, my upper limit is 30. So here t is 30 into 60 seconds. So to find the alpha, we have k by rho c. So my k is 0.062. Density of asphalt is 2115 and c is 920. So on calculating, my k will be 3.18 10 to the power minus 8 meters square per second. So we just need to plug the value now. So my k is 0.062. Temperature is T minus 20 pi 3.18 10 to the power minus 8 2 into, this is my time, overall time 1 by 2. So now on just calculating it, we will get the heat transfer 4.9 10 to the power joule per meter square. So here in this question again, we treated the body as a semi-infinite body. So we use the same expression, but in the question they asked to find the total heat transfer over the entire 30-minute period. So we integrate from 0, time equals 0 to time equals 30 minutes to calculate the overall heat transfer over that period. Any doubt in this question?
Actually, sir, that expression, that the first original expression, that pi in the denominator, square root pi alpha t is there.
Yeah.
So what is that time? That time is that, and any time, why we are integrating it?
So
because that expression is for semi-finite surface. Already we know it.
yeah, so here we assume the surface to be semi-infinite solid. I just want to solve this type of question related to the semi-infinite body. That's why I use this assumption. Otherwise, in the question it will be given, like in the previous question, it is given that to treat the body as a semi-infinite solid. So in the question it will be given. Here I just want to solve one example related to that concept. So here t is the instantaneous time, which means at time t, what is my instantaneous heat transfer? But if you want to find the total heat transfer from the beginning, from the starting point to the end time period, you need to integrate it over the time. So here we have done the same thing to find a total heat transfer from the beginning to the end of the time, which is 30 minutes. We integrate it over the time from 0 to 30. If we don't integrate, we can just substitute here t as a 30 and we can get the instantaneous heat transfer at that time. That's it. But to define the total heat transfer, we need to integrate over the time. So this is the heat transfer from time is equals 0 to time equals 600 seconds. So heat transfer, there will be heat transfer at time equal 1, at t equals 2, t equals 3. So till 600, the overall heat transfer. So this is the overall heat transfer at each subsequent time till 600 seconds.
So sir, even if we are having time 0.1 second we want to calculate, let us say 1.
Yeah.
1 second. Even then, we have to integrate this expression because then,
If you want to calculate the total heat transfer from 0 to 1 second, then you can integrate it. But if you want to calculate just a heat transfer or the instantaneous heat transfer at 1 second, then you can just use the above relation. For total heat transfer, overall heat transfer over the entire period of time, you need to integrate in time.
okay, sir.
Yeah. So let's move to the last question of this topic. So in this question, and so this question is related to the long body or the non-uniform heat conduction. So in the lumped analysis, we assume that inside the body, the temperature variation is uniform. And in that case, my Biot number will always be less than 1. And so we can use the lumped heat transfer analysis to solve the question. But in this question, we will see that the variation of the temperature inside the body will not be uniform. So the question is, an ordinary egg can be approximated as 5 centimeter diameter. The egg is initially at a uniform temperature of 5 degrees Celsius and is dropped into a boiling water at 95 degrees Celsius. My heat transfer coefficient is 1200. Determine how long it will take for the center of the egg to reach 70 degrees Celsius. So there is nothing about semi-infinite body, so we will not treat this question as a semi-infinite body. We just need to calculate the Biot number to see if it can be solved from the lumped heat transfer analysis or not. Share by K. And since it is a spherical, we have everything here is in SI unit. My radius is 0.025 and my conduction conduction coefficient is 0.627. So on solving this, we can find our Biot number is 47.8. Hence, we cannot use lumped heat transfer process. Further, we are not treating this as a semi-infinite body also. So in that case, we need to solve this problem by using charts, by various charts. So let me write some temperature profile for basic shapes. So if it is a plain wall, my temperature profile will be. So you can find this expression in any standard textbook. So this expression is valid for walls, sphere and cylinder. Here A and lambda is a coefficient and you need to determine the value of A and lambda through charts, through various charts. You can use, it is given in any textbook and in case if it appears in any exam, any competitive exam or in college exam, they will give some data from the chart to see the A1 and lambda 1 value. So first, let's calculate the lambda one and A1. So we have a Biot number of 47.8. So our Biot number is 47.8, and we have given a spherical geometry. So this is the chart I'm talking about. So we need to consider for the spherical geometry for this. So we need to look into this column. This is my lambda 1 and A1. And we need to look for biot number 47.8. So which will be lie down in this region. So this is my biot number. So my lambda 1 is, let's say, 0.307.5 approximately, and I'm guessing my value of A1. This is my A1 approximately is 1.995, because I need a value between this and this, because my biot number is 47.5. So I need a value between this and this range. So here my A1 is 1.995 from the chart, and lambda 1 is 3.0753, and this is my time constant, and I need to find this time constant. So just plug into this equation 1. We already given the temperatures. Tau, and on calculating this expression we will get tau as 0.209. Now tau is a non-dimensional time here, which can be given as T alpha by R naught square. So this is my definition of tau, which is valid for all the shapes: sphere, cylinder, and wall. So I need to find the time. So time will be tau R naught square alpha. So my tau is 0.209. My radius is 0.025, and my thermal diffusivity is this. So on calculating, I will get time as 865 seconds, which is 14.4 minutes. So in this question, we need to define a time at which the temperature will reach the 70 degrees Celsius. So we already have all the temperature given, and since the biot number is greater than 1, we cannot use the lumped heat transfer analysis here. And this is also not a semi-infinite body. That means we cannot use a pre-existing relation of heat transfer and temperature variation here. So we use the temperature variation for the general case when the biot number is greater than 1 and it is not a semi-infinite body. So this temperature variation is valid only for spherical, cylindrical, and rectangular geometry. And here, to find A1 and lambda 1, you need a chart. So you need to go through the book to find out the value of A1 and lambda 1. In case if it is appear in exam, they will give the value of this A1 and lambda 1. So from the chart, you guess the value of A1 and lambda 1 to find the tau here, and from this relation you find the time here. So tau is basically a non-dimensional time. So from this is a Fourier constant, also known as the Fourier constant. So from using this relation, you can always get the time in the dimensional limit, which is 865 seconds. So basically, there are 3 types of condition that may appear in the transient heat conduction process. So first thing, you need to check whether the body can be treated as a semi-infinite body or not. It will be given in the question. Then check if it is semi-infinite or not. Then if it is not a semi-infinite body, then always check the Biot number. If Biot number is less than 1, go with lumped heat transfer analysis. If Biot number is more than 1, then use this temperature variation relation and then use the charts to find the coefficient A1 and lambda 1. So this is the basic route to solve any transient heat convection process. So any doubt until now?
Sir, this BO number when you have calculated this problem,
Yeah.
note that characteristic length be d by 6 here. This RO, like
Yeah.
it should be d by 6.
Yeah. So it will be Biot number HD by 6 K. Yeah.
But you have, I think, used only the radius. So
yeah. So it will be divided by 3 then. Divided by 3. Yeah. In even if we divide it by 3, it will be Biot number will be more than 1. So yes, it cannot be.
Just I wanted to clarify that here instead of RO we should have d by 6, isn't it?
Yeah. D by 6 or R naught by 3.
Okay.
Yes, 3. So any other doubt?
Okay then, clear, sir.
Okay, then we are done with this transient heat conduction problems and for today class as well. So next week we will be solving some problem related to the Nusselt number, from where we will try to find out the heat transfer coefficient in external boundary layer flows. So there will be a specific relation for finding the heat transfer relation in terms of a Nusselt number. So Nusselt number is basically a non-dimensional heat transfer coefficient. So external boundary layer and the internal boundary layer, or the internal heat flux, external heat flux, every case we will have a specific relation for the Nusselt number, and from that we will be once we get the heat transfer coefficient from the Nusselt number, we can use that heat transfer coefficient to find the total heat transfer rate from the external or either internal boundary layer problem. So in this class we just look some basic fundamental question of heat convection and some few problems related to the transient heat conduction. So in the next, we will be diving a bit deeper into the external boundary layer heat convection problem. So that's it for today. We'll meet next week.
Okay, sir. Thank you.
Thanks.